Mr. Area, right?
Yeah.
Okay, well, we talked about the graph the other day, yeah? Actually, the day before yesterday. We talked about how to clone a graph. The clone is the fancy word for copy, yeah? But for the copy, we have two kinds of copy, deep copy and shallow copy. Deep copy is basically copying everything, yeah? Yeah? So make exactly copy. So once you put a copy, like let's say A equals 1, 2, 3, and then if we say B equals copy.decopy, or we say we can use this. This is a deep copy. So A and B both points to a list of 1, 2, 3. They are independent of each other. Yeah. So if I say A0 equals like 4, for example, it doesn't affect the other copy, right? Because it's totally independent of copies. We talk about how to clone a graph using the depth search. Yeah, depth search. The trick here is that because this graph is undirected connected graph, yeah. So we have the cycles for the graph, yeah. We have cycles for graph. So in order to avoid the endless cycles, yeah. So we have to remember. We have to remember in the hash set, okay? Hash set. So we make a node here. Look, we copy, make a node here, and then we immediately mark it as visited. And then before we clone its neighbor, its kid, its neighbors, okay? Yeah? So this is depth search. What's the other way we can traverse a graph? What's the other way? Okay. We are talking about this is depth search, yeah? Depth search, calling itself depth search. Yeah. What's the other way of traversing the graph? Breadth search. Yeah, breadth search. So let's say if I have a graph like that, if I have a graph like 1, 2, 3, 4, 5, okay. Okay. So let's say we have a graph this way. Yeah. If I given this node here, what's the breadth search order of this graph?
1, 2, 3, 5, 4.
1, 2, 3, 5, 4. Yeah, we're done. Yeah. Or you can say 1, 3, 2, 4, 5. It doesn't matter. Yeah, because the graph, right? The graph doesn't have. It's not like a binary tree. We have the left and right. Yeah, especially for the graph, you can say, okay, I visit this first, as long as it's next. Yeah, 3, 2, 4, 5. Okay. So in order to implement the breadth search, normally what kind of data structure can we use? Do you still remember?
Q.
Q. Yeah. And in Python, how can we declare a Q?
DQ.
DQ. What's DQ mean?
Double-ended Q.
Yeah. What does it mean? Double-ended.
It means you pop it from the
What's double-ended? What double-ended mean?
you pop it out from the
So we can look. Double-ended means that we can pop and push in both ends. Yeah, both sides. Okay. So let's revisit the breadth search. Okay. Okay. For example, this graph. First of all, I put the 1 in. Yeah. Okay. Now I take 1 out. So what should I do?
You should push in 2 and 3.
2 and 3. Okay, so now what should I do? What's the next to pop out?
1, 5.
Yeah, but what's to do with 2 and 3? So what should I do with 2 and 3?
Pop 2.
2 and take it. What should I do next?
4.
4. And what should I do next?
Delete 3. Yeah, and 5.
Yeah. And then 4
Yeah.
and 5. Yeah, exactly. That's the breadth search. Okay, so let's just quickly write this, and then we can see how we can clone a graph, undirected graph. Okay? What's graph, by the way? Graph? It's a data structure with the vertex and edges. Yeah, do you still remember? Yeah. Okay, so let's say let's implement this breakfast search clone graph. So we have given the node. Yeah, we're given the node. If not node, if we're given the empty thing, we just return. Yeah, easy return. Okay, alright.
Yeah.
So now we have a queue equals pq, and then we put the node in. Okay. Yeah. There you are. What you doing?
Nothing.
So now look y q, but we need to have a notebook hash set to remember the nodes we've been visiting. Yeah. So let's say at the beginning we put it a set. So this is kind of a standard template for the breakfast search using the BQ. So first we take the node from the in front of Q. Yeah, this is like Q. This is Q, and then we take it out. We take this current out. Okay, current equals Q dot pop what? Q dot pop what?
Top left.
Top left. Okay, so now we have a node. Node will be having the kids. Yeah, so we have say we have to iterate the kids of it. So for n in current, the neighbors. Yeah, the neighbors. Or we call it the children. Yeah, doesn't matter. The neighbor. Let's call it neighbors. Yeah, neighbors. Neighbors. Okay, then if n not in scene, okay, then we scene dot add n, right? And then we need to push the n to the append the n to the queue. So what should I put here? Q dot what?
Append.
Append what? Append what? What are our kids? Append what?
Kids.
Well, there is no kid. Which one is kid? And that's it. Yeah. And then we want to return. If we visit it, we want to return the root of a node. Okay. So this is just a template to visit the traverse graph. Yeah, a graph. Now we have to clone it. We have to copy it while we traverse it. Yeah. So first of all, seeing this is a set, let's change it to do I have other wait. Other colors of the pen? No? Okay, that's fine. Here. See, let's say we have a dictionary, we have a mapping, yeah, we have a table, hash table. So this one is a table. So we have a scene. So scene, this is changed from a hash set. The hash set is stores the number of nodes we have visited, but instead we wanted to store the mapping from the original node to the clone node. Okay, so the key will be the original node. The value will be the copied node. The node that is copied. So at the beginning, the node, I should give it a clone. This is let me copy it. Yeah. Look, node, the node of value, and then the neighbors will be empty list, right? So look, we have just copied one node, which is the node, yeah. So then we instead of returning the node, we return its copy, which is scene node, okay? Yeah. Now I have to do something here, right? So instead of now look, the neighbor is not being seen, so the neighbor is not being copied. So we have to copy here. So let's write here. Scene node node equals node. We copy this node, yeah. We're using this syntax end of value. Okay. Q dot append, okay. Now I have okay, so actually this needs to be moved be done when it's not seen, so I have to write it here. Q dot append n, okay. So when we only append, we only push the node back to the queue when it's not being visited, right? When it's visited, then there's no point to append it, right? So now here, at this point, we are here. So we should do what? We should put this scene n, this node, yeah, into the neighbor of the current, right? Remember this current thing, yeah, this current thing at the beginning when it's copied, it's given an empty list as a neighbor. So we have to do to this current dot neighbors dot append what? Append scene n, right? Append scene n. So because n is a neighbor of current, right? So what this is mean is that, okay, so we already know, we already make a copy of current, yeah, make a copy of current which is stored in the scene current, right? Remember this hash map, this scene, yeah, the key is this original node, like a node, and then the value will be the copied node, right? So this is node of value, yeah, okay. So scene current, this is the copy of the current node, and its neighbor needs to append scene n. And look, n is the neighbor of current, right? Yeah, look, n is the neighbor of current. Okay, so what's its copy? Scene n is a copy. Scene n is a neighbor of scene current. Yeah, simple as that. Yeah, look, the original node is current. It has a neighbor n, right? So I'm already I copied this current to scene current, right? So I already copied n to scene n. So what's left to do? I have to append these to the neighbors of that, right? Make sense? You see, this is the graph. I copy this 1, 2, right? This is original. Now I copy another node which is 1 dash. And I copy another node which is 2 dash. This is n. This is current. So what's next? What's next? There's an edge missing, right? Yeah. That's edge missing. Look, this just copy the node. This just copy the node, right? But I have to add edge. If I'm adding the edge, how can I add in the edge? How do we represent the edges in this kind of graph? Where is the edges being added? Which one is the edge added? How do we know, one is connected to 2?
Scene.
Which property of the node? Look, node has a value and has a neighbors.
Neighbors.
Yeah, neighbor is the list of vertex it connects to, right? So here, scene current the neighbor to append scene n, which means what? Scene current has the edge connects to scene n, right? Okay. Okay, so that's how the edges are represented using this kind of graph, which is called adjacent list. Right? A vertex is a key, and the value is the list of vertex it connects to. That's the adjacent list. Okay. The time complexity is still the same, yeah. Compared to depth of search, O(n) plus m, yeah. Where O(n) plus m, where n is the number of vertex, m is the number of edges, right? Yeah, number of edges. Okay, that's it for today. Good job.
Bye.
Bye bye. Okay, that's it.